Our learning objectives for Section 1 will be to outline the historical development of chemistry as a field, provide examples of importance of chemistry in everyday life, describe the scientific method, a means by which scientists design experiments, remove biases from those experiments, and then develop laws and theories from consensus among their scientific peers. We're going to learn to differentiate between hypotheses, theories, and laws. And we're going to provide examples illustrating the scope of our science. Is it macroscopic, microscopic, i.e. we can't see it, it's so small, or is it symbolic, like the way that we write something? Chemistry is a natural science that is concerned with all aspects of matter, whether that be the composition, what is something made out of, what kind of properties can we expect that it have, what are its interactions with other forms of matter or with other forms of energy, or how can we change it to make it into a product that is going to suit us. We can talk about chemistry in a couple of different ways. We can talk about the composition of a specific substance, such as the chemistry of iron. How does iron behave? Or we could talk about the chemistry of a process. For instance, blood is made out of many different things, but there's many processes happening out, and it has its own chemistry. Going back at least 2,500 years, and most likely quite a bit more, people have been obsessed with understanding what the world around them was made out of and how they were able to manipulate that to make things better for themselves. The ancients were able to often kind of stumble across different ways of manipulating matter to make things better, whether that was extracting aspirin from willow bark or combining iron and carbon to produce steel. But they didn't have a really great understanding of the fundamentals of chemistry the way that we do now. The ancient Greeks, for instance, thought that all matter consisted of 4 elements, either earth, air, fire, or water. We know now that all matter is actually comprised out of basic units called atoms. Considering that our world is comprised entirely of energy and matter, it's not surprising that chemistry, being at least one half of that, if not more, is central to a vast array of other STEM fields. Chemical processes, the rearranging of atoms into different forms of matter, are constantly happening all around us. And it is our understanding of these processes that has allowed us to create many of the modern day products that we benefit from. The scientific method is essentially the roadmap that scientists use to investigate their subjects of interest. It begins by picking out a specific natural phenomenon that they want to investigate. Next, they formulate a hypothesis. This is a tentative explanation for what they think will occur and why they think that might be true. They next design an experiment to test the validity of their results. They're going to control as many variables as possible, while changing a single one and measuring one or more other variables. When their experimental results confirm their hypothesis, they publish these results for other scientists to review. When their results do not confirm their hypothesis, they formulate a new idea of what might be happening, and they repeat their experiments. It's important to note that the scientific method is not linear. In order to validate their conclusions, scientists must leave many opportunities for failure. When the results of an experiment cannot be consistently reproduced, or bias of the experimenters is discovered, a good scientist will always go back and reconsider their experimental design. There are 3 possible outcomes when a chemist's experimental results are reviewed by their peers. In the first outcome, further experimentation by the chemist's peers does not yield consistent results, and the work is rejected. The second possible outcome, the observations are found to be consistent, but not the hypothesis. These observations then become a scientific law. And a third possible outcome, both the observation and the hypothesis are found to be consistent. In this case, the observations become a scientific theory. Both laws and theories describe an observed phenomenon. Laws, however, have a more limited scope than theories. Laws answer the questions who, what, and when. Theories are able to answer those questions, but also give us a sense of how and why. Theories allow us to not only understand the mechanics of a phenomenon, but the reasons it occurs. The description of matter can be said to lie within one of three different domains. The macroscopic domain is all the things that are large enough for us to directly see and feel and touch all around us. The microscopic domain are those things that are so small that we may only be able to see them with a microscope, if even then. And the symbolic domain contains the specialized language used to represent the components of the macroscopic and microscopic domain, such as chemical symbols. Figure 1.5 illustrates the difference between macroscopic, microscopic, and symbolic domains using water as an example. Moving from the macroscopic to the microscopic to the symbolic domains, we can see that a cotton ball is itself comprised of many interconnecting fibers. Each one of those fibers is comprised of many interconnecting chains of atoms. Chemical reactions occur in the microscopic domain. Chemists observe changes that occur in the macroscopic domain, and they express those changes using symbology